Okay. Good afternoon. My name is Daniele Rizzello from Telux Explorer, a geophysical service company based in Italy. The talk of today is about a project that we collaborated as consultants for CTPTO last year, and which subject was the development of OSI forward modeling capacity for non-seismic geophysical techniques. On-site inspections, OSI use geophysical methods to detect the presence of underground nuclear explosions observables. In this context, this project aimed at the development of a range of non-seismic geophysical forward models for deep OSI observables. In this presentation, we will show the three-dimensional magnetic field mapping, gravity field mapping, electrical resistivity tomography, frequency domain electromagnetics, and time domain electromagnetics simulations of the observables carried out by means of ad hoc developed Python functions. By changing the observable parameters and also the acquisition settings, we built a portfolio of more than 800 geophysical anomalies, which is essential for the OSI survey, geophysical survey design, the interpretation of geophysical collected data, the training for surrogate inspectors, and also for the constant update of the CTPTO geophysical equipment list. The general workflow that we followed can be resumed like this. We started from an extensive iterative review about the observables, and we established parameterized the geometrical and physical parameters which can describe the observables, and at the same time we identified some realistic UNE scenarios to be simulated. After this analysis, we developed Python code which is capable to carry out three-dimensional multi-geophysical forward simulations. Therefore, we, of course, carry out the simulations for a range of scenarios, and we finally assessed the geophysical methods' effectiveness and limits for each technique, and at the end, we obtain a wide portfolio of geophysical anomalies. The first observable that we analyzed and we parameterized is a simple UNE cavity. In order to set its size, we refer to the paper by Castagnola and Carnahan in 1971 diagram, which described the radius of the UNE cavity in respect to the depth of burial for different lithologies. We considered a 1 kiloton yield occurring in alluvium as a reference, but of course from this diagram one could also consider other lithologies. The subsequent observable that we analyzed was the alteration shells around the UNE cavity and the collapsed chimney that can occur above the cavity. As for the radii of the alteration shells around the shot point, we refer to the paper by Adushkin and Leaf 2001, which provide shell radii normalized to the yield, cubic root of the yield. And as for the chimney height, we refer to the Legarec paper 1999. Once we set the geometrical parameters for these observables, we had to estimate their petrophysical parameters in order to use these parameters in the forward models that we have to carry out. So we started from the analysis of the porosities that can occur around the UNE shot point, and we refer to the paper by Adushkin and Spivak 2004. From this analysis, we identified three main shells with porosity decreasing from the UNE shot point from the cavity, and accordingly you computed the correspondent density through the Gassman equation and the electrical resistivity through the Archie's law. As for the magnetic susceptibility, we have not found any empirical relationship with porosity, so we refer to the paper from Maris 2019, where some alteration of the magnetization around the UNE cavity is hypothesized. The literature review allows us to identify 5 main UNE scenarios. One is a simple cavity. The second one is the cavity plus the alteration shells surrounding the cavity. Third one is the cavity plus the alteration shells plus a collapsed chimney which reaches the surface. The fourth one is the one where the alteration shells are together with the collapsed chimney not reaching the surface and terminating with an apical void. In this case, we also considered the possible presence of a metallic casing which serve for the emplacement. The last scenario is the one where an horizontal emplacement occurs, and we distinguish two cases, one where the horizontal tunnel is lying beneath an horizontal topography, and another case where the horizontal tunnel is lying beneath a sloping topography. So from the analysis of the scenarios and the observables to be modeled, we realized that there was a need for three-dimensional geophysical simulations. We therefore decided to develop suitable Python codes for each scenarios, and by using the open source SIMPEG libraries for geophysical simulations, which are released by UBC. And the codes we designed was suitable for geophysical instrument available at CTPTO, and was compatible with the relevant input and output data file format. The instruments that we considered are those listed here. The output files produced by our routines are ready for possible geophysical inversion. And last remark is that, of course, the developed code was released to CTPTO. Now I will show you the results for a series of scenarios, and for the sake of time, I will not describe all the slides that are included in this presentation. Of course, you can find them. The first one is the one where the cavity is surrounded by alteration shells. And in this case, the forward modeling has been carried out by changing these parameters: the depth of burial, the cavity radius, and accordingly also the radius of the shells, the density contrast between the shells and the background, also considering dry and saturated rocks. 2 minutes only? Oh, I have to fly. The magnetic susceptibility contrast, the magnetic field inclination, and the electrical conductivity of the shells and the background. This is an example of the results that we obtained for this kind of scenario. On the right side, you can see the geophysical anomalies plots and maps. And in this case, we found that the electrical resistivity tomography is generally useful, while the gravity method is not useful because the anomalies are very, very small. The other techniques can give intermediate results. The next one is the scenario with the alteration shells, the cavity, and the collapsed chimney. And in this case, we changed the radius of the chimney, consider the electrical conductivity of the shells and the background, and the magnetic field inclination. And in this case, the most useful technique that we found was the magnetic method, while gravity again is not useful. For this scenario, we considered all the same petrophysical parameters as the previous one, plus the presence or the absence of a metallic casing. On the right, you can see the discretization of the model in the presence of the casing. In this case, the best technique that in theories should be used for this kind of scenario is the electrical resistivity tomography, and the gravity is not very useful. And the other techniques can be useful. For instance, the time domain electromagnetics can be useful if the alteration zone is shallow. Anyway, if in the presence of a metallic casing, this will dominate the response. This is the last scenario, and in this case, you can observe that beside the presence of the horizontal tunnel, we also include in the model metallic rails and metallic doors, which seal the underground shot point. And to carry out the simulation, in this case, we changed the slope of the topography, the electric conductivity, and the magnetic inclination. For this kind of observables, for this scenario, there are two methods that are useful. One is the magnetic method. It is suitable, in theory, up to 20 degrees slope, and time domain electromagnetics, which is useful in all cases. So I conclude, so I will be on time. So we developed a comprehensive geophysical simulation study of synthetic underground nuclear explosion scenarios. And the computation has been done by means of ad hoc developed Python codes, which could be useful also on site during the OSI. We built a portfolio of 870 physical anomalies stemming from 358 models and multiple acquisition settings. This portfolio is essential for OSI geophysical methods choice and choice of survey design and site acquisition strategies. The interpretation of the collected geophysical data, the training for the surrogate inspectors, and the CTB-TVO equipment list development. Thank you.
Thank you very much. We are allowed to have only one question.
Yeah, thank you very much. Interesting presentation. I was just wondering how you decided on the thresholds for what's detectable and what isn't.
Experience.
Because
Essentially experience.
I think something 100 microgals, I would be very disappointed if I didn't detect that. 100
is very high. I mean, when gravity is not detectable, you are looking at something that is less than 1 milligal, 2 milligal anomaly. So
microgravity, you'll get something 10 microgals easily.
Yeah, but in real life it's different because we are also geological noise. So we have not. We have also, beside the anomaly due to the observable, you have also other sources. So you cannot be sure that you are looking just at that.
Sure, you're always going to have noise, but I think I think they're a little pessimistic in a few places.
Yeah. Anyway, thank you.
Thank you.